Welcome to module number 31. And in this module, we're going to cover weak bases. Last module, we did weak acids, so now it's weak bases, and then we're going to put the acids and the bases together and see what happens. Okay, we're going to end up calculating them by multiplying them together, and we're going to get Kw. Okay, so we're going to start on page 45, goes to page 48. All the way up until 45 to 47 are fairly easy, and then page 48 is the one that's a little bit tricky. So I'll stop you just before we explain that, and I'll get you to read through it first, and then I'll explain it in a couple of minutes, and then we'll revisit the page again at the beginning of Friday's module. I also have a little video down here that I want to just show you parts of it because I did a demo for my grade 10 class, and it looks at universal indicator in with some milk of magnesia and adding acid to it. And it really shows you visually, because of the indicator that's there, when it's an acid or a base, and it really pushes that equilibrium back and forth. So it really goes with our topic, but I've already done it for the grade 10, so I'll let you watch it. Okay, so here we go. Some compounds behave as weak bases, proton acceptors, when you place them in water. So you'll notice that when you've got your equilibrium expression for these weak bases, water is included as one of the reactants, and it shows you what it does. It acts like a base. In other words, it is strong enough to pull a hydrogen ion from the water and attach it to that compound that you've got right there. So what we're going to be looking at are some of the salts that get formed, and then what happens to these conjugates. Okay, so just to start it off with, we know how to set up an equilibrium expression, and we can write down what the K value will be. And note for these ones, the general equation for the dissociation of a weak base in water will be set up as such: the concentration of your products over the concentration of your reactants. Remember, water doesn't have to be added in because it's liquid form, and we've never added that in before. So we're good to go. You'll notice that in this equation set up right here, B is the weak base. So you would recognize that from your list of weak bases because you memorize the strong ones. By default, the other ones are weak. And then water is acting like the acid. Remember, so water is going to act like the proton donor. Because the base is weak, it can actually pull apart the water. So we'll get to some of that terminology in a bit. Okay. Everything else is good here. So what's a question look like? Okay, so here we go. Question number 1. And again, you don't have to print off any of these pages because just work through a few examples. So what is the pH of a 0.29 mole per liter solution, and you're given the Kb? So what would you do to start that? Well, you've got to figure out what the concentration of the hydroxide ions are going to be. Can you do that? Okay. Well, you're going to set up an ice table, aren't you? Okay, so you're going to have your expression, and then you're going to calculate or set up the formula for Kb, and then you're going to do an ice table. So I'm going to skip to the answer here and just talk your way through it. Okay, so what are we solving for? We're solving for the concentration of the hydroxide ions at equilibrium. So that is this value right here on my ice table. That's what I'm solving for. Once I know the concentration of the hydroxide ions, then I can use one of those pH formulas that we have on our previous pages, where we can take the pH plus the pOH gives me 14. We'll be able to work our way backwards for that, okay? So to get us started with, we're going to pop in our original concentration. We know that these two are 0. So then the concentration of my CH3,3N is going to go down by a factor of X. On the other side of the equilibrium equation here, you're going to have those go up by a factor of X. What's the X? Well, let's assume that it's very small. And here again, we're going to make that assumption so that we can do some math that's a little bit easier. So we'll hope that it works. We can always go back and check it, right? We can just work our way back and have a look at the value. Is it a lot less than 0.29? If it is, then our assumption is okay. And if it's not, we may have to use the quadratic formula. All right, so let's substitute these values into the expression. And we get a value of 4.6 times 10 to the negative 3. Is that a lot less? Yes, our assumption is valid, so we're good to go. Calculate the validity of it. And yes, we understand that it's weak because it hardly dissociates at all. How much of it? Well, you could look at that by taking the moles that dissociate over the total moles that were available, and only 1.6% got dissociated. That is by definition our definition of a weak base. Okay? So now what do you do? Now we have to actually take that value and calculate the pH of this solution. So yeah, we're still going with the same question here. Two ways to be able to calculate it. Both ways are shown. So you could do pH is negative, the pOH is equal to the negative log of that concentration. So pop your concentration value in and calculate it. Remember that if you've got 4.6, you're counting this value here as two significant digits, which translates into 2 decimal places for the pH. You could also recognize that the pH plus the pOH equals 14, and so you could just substitute it in, subtract it from 14 and calculate it, or you can use method number 2, where you know that Kw is equal to the concentration of the hydrogen ions and the hydroxide ions. Figure it out that way. You'll get the same answer. So however you want to do that, you can. All right, now what do we recognize about this relationship? So I want you to look at this. This is a little bit tricky here, and then the second page is even trickier. But there is a relationship between conjugate acid-base pairs. Okay, do you remember that? That conjugate acid-base pairs we did at the very beginning of this unit. We've talked about it a little bit as we go along here. We're reviewing. Let's look at what's the acid and what's its conjugate. Let's look at the base and what's its conjugate. Okay, so here we go. Let's consider acetic acid and its dissociation in water. This acts like an acid, proton donor. What does it turn into? That's its conjugate base, okay? These guys are partners. There's my acid, there's my conjugate base. What was my other acid-base pair? Water, in this case, acts like a base, proton acceptor, and this, our hydrogen ion concentration right here, is what my conjugate acid is going to be. Once I've taken my weak acid and got its conjugate, I'm now going to take this conjugate base and see what happens to the conjugate base. So follow along. This value here is going to come down here. How does this conjugate base act with water? It acts like a base, okay, and produces the acid. That's its conjugate acid, right? We've already been over this. Here's my acid. There's my conjugate base. Okay, and if you put those two together using my Ka and my Kb expression that are written right beside, you get a very interesting result. You get Ka times Kb equals Kw, because it's the concentration of those hydrogen ions, or the hydronium, multiplied by your hydroxide ions. And we know the value for Kw. Right? That's a constant that we know at a particular temperature. So therefore, for an acid and its conjugate base, here's the summary statement here, the trend, if you will. Okay? Kw equals Ka times Kb. For an acid and its conjugate base, the strength of an acid's conjugate base can be mathematically quantified because we know that, and then there's a relationship here. What's the relationship? There's an inverse proportional relationship between them, okay? So for the first one, if this is the Ka value, the Kb for its conjugate, you could calculate that. And then what do you realize with this trend? As you increase the acid strength, you are decreasing the conjugate base strength. So there's an inverse relationship there. So what's the relationship between an acid and its conjugate base? The above data indicates that the strength of an acid and its conjugate base are inversely related. The stronger an acid is, it's going to have a bigger Ka, the weaker its conjugate base is. Likewise, if you've got a strong base, it's going to have a large Kb and it's going to have a weaker conjugate acid. Okay, so this is the summary right here that you want to think about. This is going to take us into the next page number 48, but what I want to show you right now is I'm going to make this video into two different parts. I'm just going to show you the YouTube video of my grade 10s. We're going to play a little clip right now because it is the neutralization reaction where it pushes it back and forth, okay? And then I'm going to pause the video and I'm going to do page 48.
Green. What color does it turn when I add it to
So we're just adding
acid? Do you remember? Red. Okay, let's add a little bit more.
That's the universal indicator in some hydrochloric acid.
I'm going to turn on my stir bar. As I turn the magnet on, it's just helping to stir it.
Okay, I'm going to skip it ahead a bit where you just add the milk of magnesia. It's just weird to watch a video in a video.
And the more you add in, it's going to push it back towards the acid range. So here I go. And now I've got more acid than base. So what do? Let's add a little bit more base. And again, this is my, oh, you can see it's already, as the time it mixed, sometimes it changes color and then all of a sudden it keeps adding to it.
It's dissolving as it's going, so it'll do that.
More. And as it's starting to work, look at.
Okay, so I'm going to pause it right there and you can watch that video too if you'd like for another little quick demo, okay?